Now we're going to look at the rate law. All right, the rate law is a mathematical expression that is going to express the relationship of the reaction rate to the rate constant and the concentration of reactants to some power. Okay, yeah, I don't know what that means either until you look at it, and then you can see what's going on here. Let's look at our general reaction. A moles of A plus B moles of B goes to C moles of C plus D moles of D. The rate law will take the form. So this is the form of the rate law. The form of the rate law is rate equals the rate constant times the concentration of A to some power X times the concentration of B to some power Y. That is the form of the rate law. And note, this is a peeve of mine. Make sure you get it right. When I say what is the rate law of this reaction, or what's the form of the rate law for this reaction, you must include rate equals. This is an equation. Rate equals. For example, if I asked you what's the equation for a straight line, and you said mx plus b, it's kind of wrong. The equation for line is y equals mx plus b. You have to have the y equals in there for equation for a straight line. By the same token, what's the rate law? Rate equals k times concentration of A to x times concentration of B to y. You must have that rate equals in there. Okay, so note that we're looking at the rate of the reaction, and we're only looking at our reactants, A and B. We're looking at A and B. And also note that X and Y are not little a, little b. These are not the stoichiometric coefficients. We will find out later by chance, or by the way it works out, they might actually happen to be the coefficients at some point. However, by looking at a reaction and looking at the coefficients, you cannot put the little coefficient A here for X and little b here for Y. You cannot do that. The only way to determine X and Y is by running an experiment. And that's what we want to do. Basically, when I say, okay, here's the form of the rate law, just given any reaction written in a book, you can say, okay, the form of the rate law is going to be rate times the rate constant times concentration of one reactant to some power X times concentration of the next reactant to some power Y. Just by looking at the equation in the book, you can come up with the form of the rate law. But the question is, what's K? What is X? What is Y? What are these two numbers here? And you need to run an experiment to actually get the true rate law, not just the form of the rate law. All right. So, however, let's look at some more terminology here. When we look at X and Y, each one of X and Y is called an order. So A is to the order X, B is to the order Y. But if you add the X and Y together, you get the reaction order, the order of the whole reaction. All right. So how do we determine X and Y? What experiments do we need to run to find out both X and Y and determine what K is? And it's really pretty simple in theory. It can get complicated to do it in practice, but this is the deal. You need to run the experiment, and if I have two variables, I have X and Y, I need a couple of equations. So I need to run the experiment at least 3 times here. With 2 concentrations, I need 3 times, or with 2 reactants. And look what happens to the rate. I'm going to change the concentration of the reactants as I run the experiment the next time, and I'm going to see how changing the concentration of the reactant changes the rate of the reaction. All right, so here's an example. Here is what we would do. Here's our reaction. F2 gas plus 2ClO2 gas goes to 2FClO gas. There's our reaction. I want to know what the rate law for the reaction is. Now, right away, I can determine what the form of the rate law is. Just by looking at the reaction, I know, okay, the form of the rate law is going to be rate equals K times the concentration of F2 to some power X times the concentration of ClO2 to some power Y. There is the form of the rate law, and just by looking at this reaction right here, I know that that's the form of the rate law. But when the question is determine the rate law for this reaction, it's asking what's X, what's Y, and frankly wants to know what K is also. So how do we do that? Because note, X and Y are not necessarily 1 and 2. We have to determine X and Y experimentally. Here's how we do it. I've got 2 reactants. I need to run 3 reactions. You always need to run 1 more reaction than the number of reactants you have. So since I'm setting this up, I'm going to start with nice numbers here. And I like numbers that have 1s in them because math with 1s is easy. 1 times 2 is 2. 1 times 5 is 5. Gotta love 1s. All right, so I'm going to set up a reaction. My initial concentration of F2, my first reaction here, this represents one reaction condition right here, one set of conditions. My concentration of F2, I'm going to start off with 0.10 molar because I like easy math. Yes, I could have chosen 0.2716 molar, but then my math isn't easy. So I'm going to choose 0.10 molar for my concentration of F2, and my concentration of ClO2, I'll choose 0.010 molar. I'm changing these numbers up a little bit so it's a little bit more easy. When I said 0.1 or 0.01, you'll know which one I'm talking about. So concentration of ClO2 is 0.01 molar. And so those are my initial concentrations. I run the reaction. Realize in the lab, you will run this reaction. You will generate a table of concentration versus time. You will plot the graph of concentrations versus time. You'll put that in a computer and get an equation. You will do calculus on that equation and then find the instantaneous rate at time equals 0, our initial rate, and that's what goes into there. Good news, on an exam, you'll be given the initial rate. You don't have to run all of that stuff. If you're in a lab, actually in the laboratory, we actually run these reactions and you have to do all of this stuff. All right, but here are my initial conditions, and here's my initial rate under the concentration of F2 being 0.1 molar, Cl2 being 0.01 molar. I get a rate of 1.2 times 10 to the minus third molarity per second as my rate, initial rate. Then I run the experiment again, but I need to change the concentration of one thing. Recall in science, you only change one variable at a time. If we have 2 variables and you change both of them, you don't know what caused the change. So I'm going to leave my concentration of F2 at 0.1 molar, and my concentration of Cl2, I'm going to bump up to 0.04 molar. Note that's 4 times. I kept my concentration of F2 the same, but bumped up my concentration of Cl2 by a factor of 4, just because I felt like 4 is a nice number. All right. Then I ran the reaction again, and when I calculated the initial rate, it is now 4.8 times 10 to the minus third molar per second. Now I need to run the reaction again because note, between 1 and 2 I kept the concentration of F2 constant but changed the concentration of ClO2. I now need to change the concentration of F2, but my concentration of ClO2 needs to be one of these numbers I've had before. And since I like 1s, I'm going to, my third reaction, I'm going to have the concentration of ClO2 be back to 0.01 molar like it was with the first one. But I'm going to bump up my concentration of F2 to 0.2, double the concentration of F2. Keep the concentration of ClO2 as the same as the first reaction. Run the reaction, do the calculus, and I find out my initial rate is 2.4 times 10 to the minus third molar per second. Okay, what does that mean? What can I get from this? Well, here's the deal. And there's some really not very too hard math that you can use to find the answer, but I prefer to use even easier ways. All right. So, next thing, Write the form of the rate law. Well, we did that already. Rate equals K times concentration F2 to some power X, concentration CO2 to some power Y. We're going to look at X and Y, figure out what X and Y are by looking at the experiments. Recall, if I compare experiments 1 and 3, well, let's go back to 1 and 3 down here. Note, with 1 and 3, experiment 1, experiment 3, I doubled the concentration of F2. Concentration of Cl2 remained the same, therefore any change in the initial rate is totally due to F2. I doubled the concentration of F2. What happened to the rate? Oh, well, 1.2 times 10 to the minus third times 2 is 2.4 times 10 to the minus third. So note, when I doubled the concentration of F2, the initial rate also doubled. And that's what we're going to be doing in this. We're going to look at, okay, I changed the concentration, what factor did I multiply my initial concentration by, and what factor did the rate get multiplied by? So, when we compare experiments 1 and 3, concentration of F2 doubled, the concentration of Cl2 was constant, but the rate doubled. Doubling the concentration of F2 doubles the rate, which means doubling the concentration, multiplying the concentration by 2 to some power X meant multiplying the rate times some power 2. And that's what we're going to do here. What did you multiply the concentration of A by times X will equal what the rate got multiplied by. We multiplied the concentration of F2 by 2, we doubled it. The rate doubled, means it got multiplied by 2 also. 2 to the X equals 2, and hopefully you can solve that. 2 to the X equals 2, X equals 1. All right. X equals 1, which means the reaction is first order in F2. I now know that this X up here is 1, because doubling the concentration of F2 doubled the rate. 2 to the first power is 2. All right, well, now let's look at experiments 1 and 2. And when we look at experiments 1 and 2 back here, we're looking at the concentration of ClO2. Note, we multiplied the concentration of ClO2 by 4. We quadrupled the concentration of ClO2. What happened to the rate? It also got multiplied by 4, which means that multiplying the concentration of Cl2 by 4, 4 to the y equals what we multiplied the rate by. Yeah, what we multiplied the concentration of Cl2 by to the y power equals what we multiplied the rate by. 4 to the y is 4, y is 1. So now we see this reaction is first order in ClO2 also. So now we can write down our rate law. Our rate equals K times the concentration of F2 to the first power times the concentration of ClO2 to the first power. Note that anytime we have anything to the first power, we don't worry about it, because anything to the first power is just that thing. So we're not going to write a 1 here. If there's a 1 for X and a 1 for Y, we do not write it in. It's just by convention, because everything is to the first power. All right, but note our reaction is first order in F2, first order in ClO2, X plus Y, 1 plus 1 is 2. So overall, our reaction is second order. This would be a second order reaction. And then now that we know this, we can actually calculate K, our rate constant. And you can choose any one of these experiments, and since I like 1, the number 1, I'm going to choose this first experiment right here, where my concentration of F2 was 0.1, concentration of ClO2 was 0.01, and our initial rate was 1.2. You just plug these numbers into the rate law. Because now I know for my rate law, rate equals K times concentration of F2 to the first power, concentration of ClO2 to the first power. So our rate from experiment 1, 1.2 times 10 minus third molar per second equals K, the rate constant, times 0.10 molar to the first power is 0.01, times 0.01 molar to the first power, 0.01. And doing a little math here, basically dividing both sides by 0.1 molar and 0.01 molar, and note the units get a little crazy. K, our rate constant, equals 1.2 molarity to the minus 1 seconds to the minus 1. Look at the units. Molar per second divided by molarity is molarity to the minus 1 second to the minus 1. So there is K. A second order reaction, a second order overall reaction, will have a rate constant in units of molarity to the minus 1 second to the minus 1. But no, that's what we've done here. So by running the experiment a couple of times, changing concentrations, we now have determined X and Y. We now know our rate law, and then we can also go ahead and calculate K. Now when we write down our rate law, we normally just put K in there. Instead of actually writing the constant in there, normally we just put in K, but it's good to know that you can get that constant. All right. On the next video, we will go through an example of this because you'll be doing this a number of times on the next exam.